You know that humble, blinking box on your desk, the network switch? Ever stop and wonder what's really going on inside? It's definitely not just a simple splitter. No, every single microsecond, it's making a whole series of incredibly fast, intelligent decisions. Today, we're going to pull back the curtain and really get into the logic of LAN switching.
All right, so here's our game plan. We'll kick things off by thinking about the switch as a smart traffic director. Then we'll take a look under the hood at its hardware. After that, we're diving into its core two-step logic, exploring a really critical trade-off between speed and getting it right. And finally, we'll follow a single data frame on its entire journey.
So first things first, we need to completely upgrade how we think about a switch. It is so much more than just a passive hub that just kind of yells data everywhere. A better way to think about it is like a super smart, highly efficient post office just for your local network. And this image right here, it really nails the switch's main job. It's constantly learning, building this map that connects its physical ports to the digital addresses, the MAC addresses, of every device plugged into it. And it lives by one golden rule you can see here: a frame never leaves the same port it came in on. That simple idea is absolutely crucial for preventing those network-killing loops. So you gotta be asking, how in the world does a switch make thousands of these decisions every second without even breaking a sweat? Well, the secret isn't some general-purpose computer brain. It's all about highly specialized hardware. So let's pop the hood and see what's making all this magic happen. Just look at how these components are laid out. It's all about pure, unadulterated speed. Data comes flying into what's called an ingress port, it hits a buffer for a split second, and then the forwarding engine just takes over. Now, this engine is the real heart of the operation, and it has two key parts we can think out as the switch's brain and its muscle. Okay, so let's talk about the brain of this thing. It's the CAM table, sometimes called the MAC address table. The best analogy? It's like a reverse phone book. Instead of looking up a name to get a number, the switch looks up a destination MAC address to find the exact physical port it needs to send the data to. This is what makes those precise one-to-one or unicast conversations possible, instead of just flooding everything to everyone all the time. So if the CAM table is the brain making the plan, the ASICs are the lightning-fast muscle that gets it done. These are custom-built chips, and the switching logic is literally burned right into their circuitry. A normal CPU would just completely choke on this amount of traffic, but ASICs, they use these hard-coded paths to process frames in parallel, which is how they bridge that gap between the logic of what to do and the raw wire speed performance to actually do it. Okay, so we've got the hardware down. Now, how does that hardware actually think? Well, it all comes down to this beautifully simple but incredibly powerful two-step loop, and it runs this loop for every single frame that comes through its doors. So step one is all about learning. You can think of the switch as just being a quiet observer, a student of the network. When a frame arrives, the very first thing the switch does is look at where it came from. And here's the really cool part. The switch learns where devices are by listening to where they speak from. It grabs the frame's source MAC address. If it's a totally new address it's never seen before, boom, it adds it to the CAM table. If it's an address it already knows on that same port, it just resets a little timer. And if it's a known address that suddenly shows up on a new port, the switch is smart enough to update its table, figuring out, hey, that device must have moved. All right, so the switch has done its homework, it's learned something from the source. Now it can act. Its second question is the active one. Okay, I got it. Now where does this thing need to go? This is the forwarding decision. And you can see that logic right here. It's super efficient. The switch reads the destination MAC address and checks its CAM table. If it finds a match, a known unicast, it sends the frame only to that one specific port. Total precision. But if the destination is a mystery, or if it's a broadcast that's meant for everyone anyway, then it has no choice but to flood the frame out of every other port. Okay, but here's where it gets really interesting. How the switch actually forwards that frame isn't always the same. There's this fundamental engineering trade-off going on here, this constant balancing act between being crazy fast and being absolutely positive the data is perfect. This slide perfectly compares the two main philosophies. On the left, you've got store and forward. We can call this one the perfectionist. It patiently waits for the entire frame to arrive, stores it, runs a full error check, and only then sends it along. On the right, you have cut through, the speedster. It reads just enough of the frame to see the destination address, and whoosh, it's gone, on its way. Speed is everything. So when would you use one over the other? Well, this table lays it all out pretty clearly. Store and forward gives you that high reliability. It makes sure bad, corrupted data gets dropped, which is perfect for a general office network. But cut-through, that's all about ultra-low latency, which is what you absolutely need for things like high-performance computing or financial trading, where every single microsecond counts, even if it means taking a tiny risk of passing on a bad frame.
Okay, we've got all the pieces now, right? We have the hardware, that two-step logic, and the different ways to forward. So let's put it all together and trace the complete journey of one single frame as it makes its way through the switch. Okay, let's watch this happen. A frame zips in on port FAW1. First up, learning. The switch sees the source MAC address and immediately adds an entry to its CAM table, mapping it to port FAW1. Next, the decision. It looks at the destination MAC address. And nope, it's not in the table. And the result? Because the destination is what we call an unknown unicast, the switch has to do the only logical thing it can. It floods the frame out of all the other ports, basically yelling, "Hey, is anyone out there looking for this?"
And there you have it, the whole elegant cycle from start to finish. The switch uses its CAM table to map the entire network. It builds that map by learning from the source addresses coming in on ingress ports. It then uses that map to forward frames to their destination through an egress port. And it does all that using a specific method, either store and forward or cut through, that's been chosen to be the best tool for that particular job. So all of this leaves us with a really important question, especially today. As our need for speed just gets more and more insane for things like AI and real-time analytics, we have to constantly rethink this trade-off. When is good enough and incredibly fast actually better than perfect but slow? The answer to that question is what's shaping the future of network design right now.